Hi, my name is Nicola Anderson. I'm a postdoctoral researcher at the Brain, Attention, and Reality Lab here at UBC in the psychology department. And I'm going to talk to you a little bit today about eye tracking in VR and a little bit about our ongoing projects and plans and some very, very preliminary eye tracking data. So just, bear with me on the preliminariness of that. We just got it in, so. Okay, so who are we? The Brain, Attention, and Reality Lab. Well, we used to be called the Brain, Attention, and Research Lab, but we changed it to reality because we would like to understand cognition as it happens in the world, and in a world that is rapidly changing, especially in terms of technology, and to understand basically how cognition works in the real worlds and in virtual worlds and in augmented worlds and things like that. So to do this kind of work, we combine natural and real-world observations of behavior and cognition with lab-based investigations. That's basically us. And what we have recently, actually last year, acquired as an SMI HTC-Vive eye tracking head-mounted display. And it is it's really great because it's quite fast. It tracks eye movements at 250 hertz, which is pretty good. And we can track both eyes. It has both Unity and Unreal plugins and quite high resolution. So I'm sure a lot of you have used the HTC-Vive, so you know it actually feels pretty good. The really terrible thing is that it was SMI has just been bought by Apple. So we have done most of this work without any developmental support and all of this stuff, and actually our laptop just broke, so we're trying to track down the warranty from a company that doesn't exist anymore. So anyway, we're working through the issues, we're getting there. So to get the eye tracking part of the HTC-Vive working required a computer scientist named Walter Bischoff, mostly, knowledge of C#, and we used Unity, that was what we chose to use. And the concept of raycasting and multi-threading in C#. And this was just like quite a slog to get it figured out, especially given that we didn't have a lot of support, but we got there and we have it working now. And so, in this talk, I'm going to tell you about sort of what we would like to do with VR, which is two main things. We would like to understand VR as an experience in itself, so what does it feel like? How immersive is it? And at first I'm going to tell you about a project that is on that side, and it doesn't actually have eye tracking. So I know it says I'm talking about eye tracking, but it's at the end, so be patient a little bit. But I also want to talk about something a little bit more closer to my heart, which is VR, using VR as a tool for research, and specifically understanding eye movements in VR. So let's start with the first one, VR as an experience. So we all know that yawning is contagious. I think we all know that. This guy, Andrew Gallup, actually studies that as a phenomenon. He's actually an expert in yawning, which is kind of strange, but true. And so if you watch this video here, it's pretty much the case that you will yawn. So let's see who's yawning. So essentially, this is just a phenomenon that happens. We don't really know too much about it. I think Andrew knows a lot more than I do, for sure. Like, I just want to also caveat this with, this is not my project. This is something I was mostly just administrating with Andrew doing most of the work. But I think it was kind of cool, so I wanted to present it here. So yawning is contagious, except that I was watching you, and I was kind of judging you, so it's not that contagious when you actually know you're being watched by somebody, if you're in the presence of an experimenter, for example. And this can be either a real person in the room with you, or it can be an implied social presence, such as like a webcam or a camera. And so when these things are there, you just don't tend to yawn. You're not yawning in response to a video like this. So, is yawning contagious in VR, and why does it matter? What does this tell us? So there are a lot of theories about why yawning is contagious, and some of them are kind of strange. Like, for example, about reducing the temperature of your head, I think, but besides that, why would we care if yawning is contagious in VR? So let's talk about that. So the social presence effect, this idea that you reduce the amount that you contagiously yawn in the presence of others, can tell us something about the degree of immersion that you feel in VR. So if there is an experimenter in the room, are you even aware of it, given the fact that you're in virtual reality and you can't see them? You maybe can't even hear them. If you have this whole other reality, this virtual reality that you're actually focused on. So it sort of can give us a sense of how much you're aware of the outside world and how much of you're aware of the virtual world. And in addition, if we can see that people are yawning in response to like an avatar yawn, that can tell us a little bit about the avatar as a social presence itself. So this is essentially what we did. So we have this really sort of low-tech setup, which is just in Unity, just like the horizon, and there's a plane with a video of people yawning, and I think they're also laughing and smiling and things like that. And we have this, some participants saw this really creepy avatar guy who would be either looking at them or he'd be looking away slightly, like he would be obviously not looking at the participant. Some participants had this webcam in virtual reality, which would tell them was either on or off. And some participants, we would say, the experimenter would come in, they'd put the HTC-Vive on, and they'd say, okay, I'll just wait here while you go through this, and then, or the experimenter would be like, okay, you do this experiment, I'll be in the other room, come get me. So this is what we did, and then we just count the number of times participants yawned during the course of the experiment. So what did we find? Well, we found that the webcam being on or off in virtual reality made no difference in the amount of yawning. They did yawn, but it didn't matter whether it was on or off. When the avatar was looking towards or away from them, also didn't matter. But the real person being in the room, the real experimenter, did reduce the amount that people yawned. So they were, even though they were in this other environment, aware that the experimenter was there, and they modulated their behavior. And I actually just want to say beforehand, I think it's strange that people yawn at all in VR, because if you think about it, it's like this really heavy thing on your head. And I don't know, I was actually surprised that it even happened at all, but it does, so that's kind of cool. So, is yawning contagious in VR? Yes, it is. And this might tell us that VR may not be quite as immersive as we think. So we are actually aware that there's the experimenter out there, even though we can't see them. But I want to caveat that a little bit with some issues with this experiment. So first of all, a webcam in VR, what is that? Like, do you think participants actually looked at that and said, is that actually recording me? Probably not. But we didn't ask them, so that's something we can do in a future experiment, for example. Also, the avatar was completely creepy. He never moved, like he didn't do anything. We didn't tell them, anything about him, just he was standing there and participants were probably like, well, okay. And that was it. So they probably could easily ignore him, So it could be that the avatar was not quite as like a social presence as we thought, because participants were like, well, it's just a picture. That's the way they treated it. The other thing is that we didn't have participants in any kind of sound canceling headphones, so it was just like they could still hear what was happening in the lab. It wasn't super loud, but that might also enhance awareness outside of the VR. So we're still learning, and these are all things that we can actually systematically test now. But I think it's interesting. I think it's kind of interesting that this yawning can be used as sort of like an index into how immersed people are in the VR itself, which is kind of cool. So that's the VR as an experience part of my talk, and now I'm going to talk about VR, using VR as a tool for research. And this is finally where the eye tracking comes in. So okay, first I'm going to talk a little bit about the background of eye movements in VR. So I just did a quick Google search, and I came up with an article that was like, oh, eye tracking in VR, all these cool things we can do. So one of the things people think that it can be used for is that the eye movements can be like kind of like a cursor in a hands-free setup. So, you can, because you're actually holding something usually in VR or whatever, you can actually use eyes as like another, like a mouse kind of cursor. in my experience, I think that this is a little bit of a weird one because people have been trying to do this with eye tracking forever, and it's not like actually that good. People, like, we don't normally move our eyes like that, like we're forcing ourselves to, like, for example, if you're trying to look at a keyboard and you're like stare at the A and then stare at the N, it doesn't really work. And I think people are still working on it, but it's not, I don't know, I'd say this is a little bit iffy. The other thing people say is that it could be used in terms of gameplay interaction. So if you can imagine being in a game and you walk up to somebody and you look at them and then that person starts talking to you, that would feel really real. So I think that's pretty cool use for it. But I think the big one is that because vision is actually the highest acuity right where we're looking, and then towards the periphery kind of degrades. We can use this fact and the eye tracking and the eye movement data in order to selectively process just the regions where people are looking, and then kind of like ignore the rest, and helps us to save resources, I think, or game companies, I guess. And this is all great that these are things, but because the development of eye tracking in VR is quite exciting, for those of us like me who are interested in just the eye movements themselves. So this actually gives us a lot of flexibility in terms of how we can do our research. So I'll talk about what we did. So first of all, I'll give you a little bit of background about eye movement control itself. So understanding how we control our eyes is actually really important. It's kind of a big deal because so much of our brain is actually devoted to understanding or processing the visual input, and we are, for the most part, visual creatures, and we use our vision to guide most of what we do. I mean, most people use their vision to guide most of what you do. And like I just said, is the video working? Oh, great. Like I just said, the highest acuity we have is right where we're looking, and everything else kind of just blurs out in the background. And we don't really notice this because anytime we look anywhere, it's really high res, but it's a fact. And so to give a little bit of, so basically how we study this is we parse eye movement data into what are known as fixations and saccades. So a fixation is a point where you're looking right now, and it lasts about 200 to 400 milliseconds, and this is where we actually get most of the information that we're picking up from a picture. In between these fixations, you have these rapid ballistic movements called saccades. They're usually between 20 to 40 milliseconds, very quick. And you just keep doing this, and that's how you see. The nice thing about fixations is that they can be used as an overt behavioral manifestation of attention. So we know where you're looking. We generally know where you're paying attention. And I did most of my PhD studying this in terms of a paradigm called scene viewing. How do we look at pictures? So if I asked you in this picture right now, what grabs your attention? Can somebody tell me? The red roof? Exactly, thank you. Yeah, so there are two, there are actually many, but there are two main theories about why we look where we do in pictures like this. The first one is that it has to do with low-level visual features. So for a very clear example in this picture is the red roof and everything else is gray. So the red stands out. Basic low-level visual feature. But it can also be like bright and dark regions, contrast, that kind of stuff. The other sort of theory is more of like a top-down one. So you look where you do in pictures like this because it has something to do with what you're doing at the moment, a task. So if I were trying to figure out what is the best place to jump into water, I wouldn't care about the red roof. I'd be looking along the shoreline. So it's sort of the interplay between these two contrasting theories is where we're sort of at in our understanding of scene viewing, but that's rapidly changing now. But in any case, because of these ideas, we have a really, really good idea of what will happen if somebody looks at a picture like this. So this picture has been modified such that I think the left side is reduced in contrast relative to the right side. And here you can see that when you actually do the reduction in contrast, that these low-level visual features based on a map or a model on the bottom is reduced, or almost all gone. And what ends up happening is when you have a picture like that, the first eye movement that you make, the first saccade into the picture, is almost always, 75% of the time, towards the higher contrast side of the picture. And then as you make more eye movements, you kind of go back down. So it looks something a little bit like this. So you might start in the middle, you go up to the, the rooftop corner, and then down to the fence, and then you start moving back towards the lower contrast side. So this is great. So people tend to do this pretty consistently. We know it. I've seen it many, many times. And it's just, I want to note that this happens when people sit in a chin rest in front of a computer screen where they're not allowed to move their head. So why should we do this in VR? We know so much about it anyway. But in VR, it's really nice because we can move our heads, which is like, blows my mind. Because all of the work that we know, all of the things we know, most of the things we know about eye movements is really about like head static. When you move your head, or what happens, I don't know, nobody knows. So that's one of the really great things about VR, is because we can get people to move their heads. And the other nice thing about why we should use these kinds of pictures is because we have a really simple prediction. We have a new system, a new VR system. We have eye tracking data we don't really know much about yet. We want something really easy to analyze. So all we really need to do is see, did they go left or right, which is kind of nice for a start. And what we did in this project is we ended up varying the viewing distance of the picture. So the picture was either quite far, it was like about, I don't know, felt like about that far away, or it was like right here. And I guess the thought behind that, or my original thought, was like, well, if it's right up next to your face, you'll have to move your head. And I wanted to get head data. So anyway, this is what we did. We measured the eye position and the head position in space. That's eye position on the picture and head position in space. And we checked, where did they go, left or right? Before I get to that, because I'm sure it's really exciting to you guys, is event detection. So the idea that, and maybe this is useful for some of you who are thinking about getting into the eye tracking stuff in VR, because I know that there are a couple of systems just coming out now that can just be put into any VR setup, is that what you tend to get from an eye tracker is sort of positional information about where the eye is at any given moment in time for a given sample, and then the number of samples you get depends on how fast your camera is. And you can see in this picture is sort of an example of some samples from the HTC-Vive eye tracker that we have. But in order to figure out which of these samples are fixations and which are saccades, which is kind of important for comparing your data to all of the stuff we already know, is something called event detection. And it's necessary so far for all of the VR eye trackers that I know of. I don't think, like most of the time when you use eye movement stuff or eye movement tech, you get like some software that comes with it that sort of does the automatic detection, event detection for you. So I just wanted to mention this if anyone is thinking about it. For this particular project, we used a really simple technique called dispersion threshold identification. And it's very reliable. It's quite good, depending on your what you're trying to do with it. And basically what it just does is it looks through the samples for clusters within a certain radius, and it just labels those as fixations, and the rest are saccades. It also does blink detection and stuff like that as well. Anyway, I want to mention that. And I also want to show you what our first actual eye tracking data out of the HTC-Vive looked like, and this was me just looking around at little dots that I kept presenting. And it's like we've come a long way from this, but that's how it really looked like at the beginning. And it took us a long way to get to that. But anyway, there you go. Back to the question, why do we do this in VR? So again, I just wanted to reiterate, we got these pictures with the contrast reduced on one side, and we're just going to look whether people look to the left or to the right, and we're going to measure their head position as well. And here's some of the fixation data. So we did that IDT analysis, and amazingly, we replicated previous work. Not surprising to me, but you know, it seems like, so in orange you have the far distance, and in green you have the close distance, and on the x-axis you have the saccade number. So first eye movement, second eye movement, third eye movement. And then on the y, and this is the case for all of my figures, is that the higher you are, the more likely you've gone to the higher contrast side of the picture. So we have these two distances. It seems like there's a difference between the two. This is about 15 subjects so far, so it's a little bit, we're a little bit, I don't know, we still have a lot more work to do on the analysis. But yeah, it looks like when the effect is a little bit stronger when you're farther away than when you're close. And there may also be, like in my preliminary look through the data, there may also be some other differences there, but I won't go too much into that right now.
Sorry, short question in between.
Yeah.
Have you compensated for the contrast ratio you look at for the screen distance, the virtual one?
No, and actually
so
when
the actual distance or the contrast seems higher for
exactly. When I gave this talk as like a practice to my lab, one of the students was like, oh yeah, when it's farther away, isn't the contrast effect more apparent? Yeah. No, and we can do. We can do that easily. But yeah, there's something we had the pictures already. We just threw them in. We wanted to get started.
Just clarifying.
Yeah. Well, I mean, we just needed some data. So anyway, so that's a really good point, though. The head data. So this is just horizontal head rotation. People like moving their head like this. And of course, when it's closer to your face, you do rotate your head more. Except when you zoom out on the data a little bit, it actually turns out people don't move their head very much at all. So this is something that I kind of suspect of most of my participants, is that they don't really move their eyes either. They're just kind of like, oh, this is really boring. I'm looking at a picture. I have nothing to do. I'm just going to stare in the middle until it goes away, and then I can take the headset off. And but I might like, this actually makes me suspect that maybe earlier on in the experiment itself, people might be moving their head more than later, and this is all stuff that I can look at as well. Or I can give them some kind of task to do, like, they were just told to look at the pictures like they normally would, which is kind of really lame. So we could ask them, okay, search for something in the picture, or ask them a question about it later, or remember it for a later test, that sort of thing. So I know that we need to get people's engagement into this a little bit more in order to even get enough head data. But that's something that like I say, we're still learning. So one thing that I really want to get out of this data, and I don't really have it yet, this is some preliminary data. This is actually me looking at pictures and pretending like I'm a super engaged participant and moving my head actually like exaggeratedly. And we do know that when you combine eye and head data, the eye usually moves before the head does. So this is actually also happening in VR, just for me anyway. And that's something I want to look into a little bit more in the future. So lessons learned from the first eye tracking study, apologies that it's only preliminary data, is that, well, it really looks like people don't move very much when they're doing something like this in VR. One of the ways I thought we could start trying to get around it is get people to stand versus sitting, that kind of thing. And also I can even make the screen closer, or make it 360 or whatever. And the other thing I learned throughout this whole process is, and it really was a slog, like from beginning to end, is to check and double check your code, because small mistake in code can actually have consequences way down the line, we know now. And I just want to say that we are working on a proper calibration validation procedure for our eye tracker, because the stuff that came from SMI is not transparent. And so that's something that we're in the works on right now, and yeah. So the two big projects so far that we've done in VR with our eye tracker and without our eye tracker is, so when we think about VR as an experience, we're going to probably continue looking at this contagious yawning stuff, so using it as a measure of immersion. And a couple of people in our lab are sort of interested in this idea that you do have this kind of dual reality going on, where you're aware of both your real space and your virtual space, and the extent to which you're aware of one or the other could be, could have consequences to how your cognition is occurring in one or the other, and what does that look like? And so that's something that we really want to look into as well. So if anyone has ideas for projects on that, I'd love to hear it. In terms of using VR as a tool for attention research, we still have quite a long way to go. Like you saw, this is very preliminary stuff. But just answer the question: does attention and vision work the same way in VR as it does in real life, or does it look like all the stuff that we know about how it works when you're sitting in a chin rest in front of a computer monitor? And so what we're gonna continue doing is to replicate some of this really basic attention research, and also things like, for example, visual search. Like if you're looking for like a Where's Waldo kind of thing. Like we know about Where's Waldo, like how you search for him in a book, but what happens if he's behind you? Like we have no clue what that looks like in terms of eye movements or attention stuff. So we're hoping to get some of that stuff going as well, and then closer to my heart, again, looking at the combination of eye and head movements, and I'm going to start working on hopefully some interesting ways to combine the two and understand them better together. So we still have a long way to go, but we are up and running. Everything is working, except for the laptop right now is broken, but we're going to get that fixed. And we will be checking in, either me or others in our lab, with more data later on. Thank you all very much for your time. These are most of the people involved.